Yeah. I'll talk about an effective theory for warm QCD. And so when I was looking at the title of this conference, I thought it was very long. So I did the usual Indian thing of making it shorter by taking only the initials. And that looks, of course, much smaller and much more beautiful. But you may not have noticed something. This has hidden inside it a GST. And that, of course, makes it very exciting. Okay. So anyway, and today is the budget day, right? So all this kind of makes it very exciting. So let me go on to the physics here. So I'm going to talk about, so why am I going to talk about an effective theory for warm QCD? Let me remind you that the biggest sign problem that we have is that the path integral for any quantum system in real time has lots of cancellations, lots of phase cancellations, okay? So this is something that we have no idea how to deal with, and we usually deal with it by, when we want to set up a numerical method for computing path integrals, we go to Euclidean. Okay, we bicrotate to Euclidean time and take the vacuum expectation values obtained by Monte Carlo in the path integral defined in Euclidean time. And then if we want to continue to real time for some reason, then we need to exercise extreme care. For example, if we want to look at transport coefficients at finite temperature, then we would like to use, in order to do this Wick rotation back to real time, we need to know spectral functions, okay? And the spectral functions are, of course, not known a priori, okay? So we have to fit the spectral functions along with the data that we have, okay? So is this doable? People have been trying to do this for a while. And there were some initial results which were very exciting. People used Bayesian techniques to kind of put bounds on what the spectral functions could look like. But this turned out to be much harder than what we thought 10 years ago. Okay. But the problem remains very urgent because there's a beam energy scan going on at RIC. Okay, and if we want to interpret the data of that beam energy scan, and we need to understand these transport coefficients, okay? And we need transport coefficients to basically to figure out whether the QCD critical point can be reached in these experiments at all, okay? Why do we need that? Because the signals that seem to kind of most promising signals, let me say, of these, not we are at or close to the critical point, are basically checks of whether or not there are large critical fluctuations, okay? The longest ranged correlation functions at the critical point, at the QCD critical point, finite quark mass, are basically baryon number fluctuations, okay? Fluctuations in the number of quarks. Okay, they lead to divergence in the baryon number susceptibility when we look at it on the lattice. Okay, and that's how we started looking at it, and then many others now do it the same way. Okay, look at divergences in the baryon number susceptibility, which means that we are really looking for this long-range correlations in baryon number. Now, when you're looking for something like that, you're looking for transport, or when you're looking at the non-equilibrium dynamics that goes into these that is associated with these long-ranged fluctuations, you're looking at flavored currents, okay? Transport coefficients of flavored correlation functions, okay? So you're exciting quarks in the medium, not gluons largely, okay? So these, and of course you're looking at transport coefficients, so you're looking at long-distance physics, very slow physics, so momenta much less than temperature. So then the question that we could ask is, whether it's possible to do this analytic continuation from Euclidean to real time using an effective field theory. Okay, really an effective field theory, not a model. Okay, really think of writing down a theory which explains correlation functions, systematically improvable. Okay, don't worry about whether it's simple or hard, but just do it systematically. Now, there are effective theories that people have used in the past at temperatures much smaller than the crossover temperature of QCD. Very old, 1980s, people looked at ion gas models. Okay. At very large temperature, of course, there's the weak coupling QCD, which people have also explored quite early. But the interest is near the crossover. Okay. And what could we do near the crossover is the question that I'll try to give one answer to right now. Okay? So let me try to write down an effective theory. So first of all, the only thing that I'm interested in is correlation functions of flavored currents, no external gluons whatsoever. Okay? Maybe if I try to do that, I should be able to take all gluon effects into the couplings of an effective theory involving quarks, maybe. Okay? So that's the first thing that I need to check, and that will be the rest of this. So what I'll try to describe is low momentum endpoint functions at some temperature, okay, at some finite temperature, let's call it T0, okay. So T0 is a special scale, right, because that's, so momenta much smaller than T0 are soft momenta, typical momenta are, in a thermal system, are T0, okay, so we are not looking at those, we are looking at things much softer than that. So T0 will be my ultraviolet cutoff. So we try to understand momenta much less than T0 in both the Euclidean and Minkowski theories so that we are able to give a good description of screening in the Euclidean theory and then continue it to real time using this effective theory. So that's the idea. Now, of course, you know that the goals must be very limited. We cannot describe all of the theory. We have first of all put this cutoff. Okay, so many things are out of reach. In particular, the full equation of state is probably out of reach. It's almost definitely out of reach because the equation of state will involve momenta which are typically of the order of the temperature. Okay, and we're not going to worry about that. So the full equation of state is something that we're certainly not going to get out of this. Okay, the real point is to get these endpoint functions. Okay, but maybe in the process of doing that, if there is a critical point, we should be able to obtain universal parts, okay? Because if we don't get those soft universal parts, then there's a failure of universality. So that's one thing that we should be able to do. I will not do it here, but I think we should be able to do that. The symmetries that we are therefore looking at, quarks in the external states, are chiral SU2 vector cross SU axial. Okay. And NF equal to 3 just becomes a little more complicated, so I'll concentrate on 2 flavors right now. Okay. And of course, this is something that's valid at 0 quark mass. Okay, and we'll just have to explore how large the quark mass can be before the kind of effective theory description that I'm going to use will break down. Okay, so the effective Lagrangian, a mass term. Okay, so I'm going to give all dimensions in units of T0, which is the temperature around which I want to conclude. Okay, so the mass is given by this dimensionless number D3 times T0. Okay, then the kinetic term, okay, and then this other part of the kinetic term, okay. Now you notice that there's a coupling between these two. These two do not have the same normalization. And the reason I can do that is because at finite temperature, I've chosen a frame. I've chosen to work in a frame by putting a heat bath. Okay, so there's a selected frame in which momentum distributions are Boltzmann, let's say, or something like that. Okay, so Lorentz invariance is explicitly broken by putting a heat bath in contact with the system. Okay, so I have to distinguish between, I have to break all three tensors into spatial parts, temporal parts, and so on. Okay, so this constant that comes here is actually what distinguishes between pole and screening masses. You can see that if you take low energy, if you take the momentum, the spatial momentum going to zero faster than the energy, then poles in the Minkowski theory would be determined by D3, okay? But if you take the limits in the other way, take the energy going to zero first and then look at finite momenta, that's screening, okay? Then you would see a different pole in the propagator. So that's the difference between pole and screening mass. That comes naturally out of this formalism when you take into account the breaking of Lorentz symmetry. Okay, so that's dimension 3 terms, dimension 4 terms. There are no dimension 5 terms once you ask for chiral symmetry. Of course, you have this term. We know that we have this term. This is the NGL model. But since we are doing an effective field theory, we should not just stick to this term. We should adding all possible terms that we need. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay, so at dimension 6, at least 10 couplings. And then you had 2 couplings there. Okay, so lots of couplings already at dimension 6. How do we fix these? Okay, so what I'll do first is to take the mean field approximation, okay, and do the mean field approximation, take Fermion bilinears, replace them by, do the usual Hubbard-Stratanovich with the fixed condensate, do the Fiat's transformations. You find that all these couplings collapse into one. Okay, so in the mean field theory, it's not 10 4 Fermi couplings, but 1 effective 4 Fermi coupling. Okay. So the mean field theory becomes the same as you would have in normal NGL. Okay, so that's something that we know how to deal with. So that's what I've written down. Okay, now we know that in the chiral limit, when you set D3 equal to 0, you have a critical point. Okay, we know that already from previous work with NGL. Okay, so we can write down the gap equation, and if we choose our temperature T0 to be at the critical point, that's a choice, that's up to us. What is T0 is something I have to tell you. So I tell you that I'm interested in the region around the critical point, so I can choose T0 to TC. If I make that choice, and then the solution of the gap equation gives me a relation between the two couplings. This lambda, which is this effective coupling made out of all these, and the D4 coupling that we've seen. Okay. And if you were to change T0, then you would change these couplings. Okay. Can we go on? Yes. So let me just do the counting of couplings here. You had 10 couplings which collapsed to a single combination lambda. Okay. And lambda was then used to fix TC with the choice that T0 equal to TC. So this is some kind of a dimensional transmutation. Okay, lambda transmutes to fixing TC. Fixing lambda is the same as fixing TC. But TC is unknown. Okay, and also 2 leftover couplings, the mass and the difference between the pole and the screening masses, the D3 and D4 couplings are also unknown. So you have 3 unknowns. Okay, and the strategy will be to use the location of the crossover temperature, not the chiral critical temperature Tc, but the crossover temperature at some finite mass, and 2 measurements of correlation functions, to fix these three parameters. Okay. How do we do that? We match to lattice data. Okay. The crossover is fixed by finding a chiral susceptibility, looking at the position of the peak of the chiral susceptibility. That defines the crossover temperature for us. Okay. And also, if we want to fix, measure fixed couplings by looking at correlation functions measured on the lattice, then we better take gauge invariant correlation functions. Okay, long distance gauge invariant correlation functions, and the longest distance ones involve pion quantum numbers. Okay, so the matching that I do must be done not with the mean field theory, but with fluctuations taken into account. Okay, so I do the mean field theory, I'll do the fluctuations, okay, and then I will try to match the corresponding thing to lattice data. Okay, but the number of couplings to be fixed is 3 because you're taking small fluctuations around the mean field theory. No new couplings will be generated by that. Okay, and in some sense this is neat because if the temperature is much smaller than the lattice spacing, okay, then you seem to be getting continuum effective theories from some finite lattice calculation. Okay, so that would really be neat if it works out. There are, of course, caveats, and I'll show you. Okay, so fluctuations next. So, well, we take the Hubbard-Stratanovich transformation. Okay, these operators will be written in terms of the condensate and SU2 matrix. It's normally at 0 temperature, you would call that the pion field. You will call F the pion decay constant, but this is at finite temperature. Okay, so these are just fields and numbers. This number F, I don't know a priori. Okay, and these are the fluctuations. These are the same angular fluctuations that you always look at. So I'm going to work just below TC, where this makes sense. You write down an effective theory for the pions starting from here, and you get the usual terms, the pion mass, the pion kinetic terms, except that there's now, again, a difference between the pion whole mass and the pion screening mass, so you put that in there. There's a pi 4 term, and of course, cubic and tadpole terms vanish. Okay, and so now what we have gained is we can count the number of couplings, 1, 2, 3, and F4. Okay, so we have 4 couplings here, but there were only 3 couplings in the underlying Fermion theory. So there must be some relations between these. Okay, so I need to fix only 3 of these things in order to fix everything. Okay, so we do that. We compute 2-point functions here, 4-point functions here, and of course the loops need to be regularized. We do that in dimensional regularization, so there are no power corrections. Logarithms are under control. Okay, and we have results for the correlation functions. Okay, so also as a byproduct, you find that the Gelman-Oakes-Renner relation remains valid at 1 loop order in finite temperature. Okay, this may of course be violated at higher loop orders. And of course C41 should vanish in the mass going to 0 limit, and we see that it does. Okay. So we match. Okay, what do we have? We don't have, lambda is fixed in terms of D4. Okay, D2 is to be fixed, D4 is to be fixed, and the only thing that we don't know now is TC, so TC is T0, so we vary T0 until we match the crossover to the value measured on the lattice. Okay, and then we look at screening correlation functions of the pseudoscalar and the axial vector, and that's enough to fix D3 and D4. Okay, right. Now, since we have gotten continuum theory, there's only one caveat. The lattice regularization gives you power corrections. Okay, so these power corrections must be taken into account. Okay, we have not done that yet. The lattice data that I've input are taken from this, and they have not looked at power corrections. So let me neglect that for the moment. So there's a caveat there. What I'm showing will be corrected later. Okay. And the second is that something that all practitioners of lattice QCD or lattice field theories are familiar with, that you measure different quantities on the same configurations. So the statistical errors that you measure have covariances. Okay, and if I read this errors off from somebody else's presentation, I don't know these covariances, they're usually not reported. So I'm forced to fix data as if they were independent, and we can improve this in future. So our errors are going to be a little large because of this, and we are neglecting some power corrections, so maybe we are making some little uncontrolled errors. Okay, so let's fix, so first thing is that TC crossover at the masses that I have access to come out to be 1.24 times T0, and given the value of T crossover that's measured by these people on the lattice, 2 flavor, it implies that TC is 170 plus minus 6 MeV. Okay, that's just the statistical. And that seems to be a little high when you compare it to 2 plus 1 flavor data, but this agrees with the chiral extrapolations for 2 flavors. Okay, so what methods have been tried before by Ove and company give us roughly the same ballpark as the extrapolation that we do using this effect. Okay, and there are 2 other inputs. One is this, I don't know why I called it U, it's C4, and there's the screening mass. Okay, these are the input values that we get from Bastian-Brandt's and company's calculation. Okay, and we convert that to the couplings that we need, D4, D3. Okay, and then of course, okay, so let me walk you through this. So each of these rectangles is what I would get by fitting this rectangle. Okay, so as I walk around the corners clockwise here, I should walk around the corners clockwise here. Okay, so D4 here, D4, D3 comes from fitting this value of U and Mi. This comes from fitting this value and so on. Okay, that's one of these rectangles here. And I get 3 different rectangles because I can use the 1 sigma lower limit, the middle, and the 1 sigma upper limit of this value. So I get these 3 things for a given regularization scale in the dimensional regularization scheme that I've used. So if I change that a bit, I get different rectangles. Okay, so that's basically the spread of uncertainties that I have from these errors, this error, and the unknown regularization scale that I have. Okay, so I fix the regularization scale. I choose the regularization scale, and then I fix some. Okay, so here's what I can do. I can use the data on the screening mass at 1 temperature, and then ask, supposing the Fermion theory had the coefficients of the Fermion theory had very small temperature dependencies, would that be compatible with the lattice measurements at other temperatures? Okay? And here's a check. So this is the data that we have fed into the fit. These are the other screening masses, and I get something that's roughly okay. Okay, you can see that I could improve this somewhat, but it's reasonable. Okay. The same thing for this coupling C4. If I put this in, then the prediction that I have with the assumption that the couplings do not change with temperature are fairly close to what the measurements are. Okay, so we are doing roughly okay. There are lots of approximations, power corrections, this temperature independence of the coefficients and so on, but they're not so bad. Okay, and yeah, F, which is the finite temperature equivalent of F pi. Okay, This is completely a prediction because this didn't go into the fits at all. Okay, and they are predicted pretty well. Okay, and we have a prediction for the 4-point function for the coefficient of the pi4 term. Okay, that's not been measured, so that's something that we plan to measure. But there's a prediction, and we could do something like that. Okay, and one interesting point is, you notice that this C4 decreases as you come towards the crossover. Okay, now whenever you look at the pressure or the energy density, you have a integration measure in your loop integrals d3p. Okay, and that C4 comes as a multiplicative coefficient in front of p squared in the propagator. So you can, when you do the integrals over the momenta, you'll have 1 by C4s, powers of 1 by C4 in front of the integral. C4 decreases as you come towards towards the crossover. Therefore, contributions from low energy, low momentum particles goes up as you come towards the crossover. Okay, that's something that was not noticed before. So phenomenological theories which try to get this rise in pressure and energy density as you come towards the QCD crossover, will have to take this one effect also into account in future. Okay, that's of course not the whole story of this rise, but that's some part of the story. Okay, so that's basically what we have figured up till now, that this kind of the most important thing is that we should be able to write an effective field theory which describes lattice computations of 2-point functions well. Okay, so that's what we have checked. I've shown you now, and we are going to use this now. We are in the process of using this to compute transport coefficients. I'm sorry that result is not yet ready, so you'll get it soon. Okay, thank you.
Questions?
Yeah, right. I mean,
constant fields or something like that.
If you take one of these things, let's say, take this as an example, put in the Hubbard-Stratanovich with a constant, okay, you'll find that this gives you a contribution which is proportional. So just the constant field gives you.
So here you have, for example, in this action, you have just broken the Lorentz invariance because of the finite temperature. Now, there are fluctuations about this breaking, which are the fluid dynamical modes. So are they suppressed in this regime, or why are we not taking them into account?
So you could take, but those would be higher dimensional operators, right? In terms of the Fermion field, you'll then be writing down higher dimensional operators.
But they would be light modes, right? And they're just modes in the effective theory. They're not, you know.
But if I want to look at.
So they won't show up in the Euclidean theory. So if you're doing Euclidean effective theory, you're fine. But in the real-time theory, they would show up as light modes. They show up.
New fields.
Yeah, yes, new fields, right? Because there are new light modes in the real time as compared to the Euclidean description, Euclidean effective theory.
Yeah, but they would still be seen as composite operators. You could still write them as composite operators in fermion fields, right? And then the power counting would reveal that, would include that.
But aren't the fluid modes lighter than the fermionic fields? That it's easier to excite the fluid fluctuation as compared to a fluctuation in the fermionic field?
But in terms of the fermion fields, okay, so if I have fermion external legs, then because I have fermion external legs, I'm building the effective theory in terms of fermion fields only, right? So the modes that you're talking about will be composite modes in these terms.
Not after you break it, right? Not after you break the Lorentz invariance. Anyway, we can, yeah.
Any other questions, comments? If not, let's thank them.